Okay, so I'm going to be talking really almost entirely about precipitation today. In light of what's going on drought-wise currently, I'm hoping that either Peter or Noah are going to hit what's really special about what's going on right now, which is to say the temperatures involved. But there is useful, well, there's a lot of interesting stuff to learn about our projections of future precipitation and the like, and how droughts versus wet periods work in California, and that's really what I'm going to walk you through today. So just to dive right in, on this figure, the brown histogram is basically annual values of the water year precipitation totals for that big red blotch over the California up in the upper right. And the black curve there is just a 5-year moving average through it. I'm going to be using 5-year moving averages in this talk mostly because it's just easier to line things up to do a certain amount of wiggle matching, I suppose, when there aren't as many wiggles. But I will show you sort of how it works out when you don't run a 5-year moving average as well. Pushing further, the same black curve's the same, the brown histogram's the same. But what's going on now, same figure, except I've broken the total precipitation out into the amount of precipitation each year that comes from the wettest 5% of days, versus, which is the red curve here, again, 5-year moving average, just to make it easier to see what's going on, versus the green curve, which is all the other 95% of wet days. And basically, what you can see, again, with the help of a 5-year moving average, is that the red curve has essentially the same, the wiggles are the same size, if you will, on this diagram. And I should say, I suppose, that if you add the red curve onto the top of the green curve, you get the black curve. So these aren't stacked in that way. I haven't stacked them already. But, so the wiggles in the red curve are every bit as big as the wiggles in the black curve, and whereas the wiggles in the green curve, which is the rest of all the other hoi polloi storms, are much smaller. And also, of course, it doesn't take much of an eyeball at all to see that, not only are the big wiggles lining up perfectly between the red and the black, but even the little wiggles on top of them are remarkably falling into line. And statistically, what this ends up looking like is that the red curve, which is those 95th percentile or the wettest 5% of days, with the moving averages applied, they capture 92% of the variance of total precipitation without a moving average applied. So if it was all histograms here, it would be 85%. And the other wet days, the statistics are shown down below, which are much less. What this is saying is that in California, our year-to-year and our multi-year sorts of precipitation variation are very much dictated. They really reflect what happens each year with our wettest days, with the largest storms. And this is very much a California thing. Like so many things that we've been looking at, when you start to look at the variability of California precipitation, it's a standout. Now, I'm not going to go into this very deeply. The upper map there is, the bright colors there are the places where you're up above 80% of the variance is explained by that top 5% of storms, and everything else is seeing much less contribution from its largest storms. And then the bottom one is just what happens with the green curve in the previous diagram. The rest of the storms, how much do they explain? And in California, you can see we're way down below 10% being captured that way. So this is very much a California thing. And now, in the title was the magic word atmospheric rivers. And I'm not going to dive into what an atmospheric river is, because if you haven't heard yet, haven't been reading newspapers, but up in the upper right there, that's an animation of the total water vapor in the atmosphere over the course of about 10 days there, I believe that is. And what you see is the bright colors are where there's lots and lots of water vapor, and you see them forming into these long, narrow tubes, if you will, where there's a lot of vapor transport. And when those hit the coast, like then, they get lifted up over the mountains, and they dump. Well, those are our big storms. They dump massive amounts of precipitation here in California. The time series shown here is a particular version of these atmospheric rivers, which are called Pineapple Express storms, which if you haven't heard about atmospheric rivers, you will have heard of Pineapple Express storms, I think. And again, 5-year moving average is the gold curve there. And you can see that it's wiggling on this sort of 10 to 15-year time scale also, which if I take it and lift it up and dump it onto the previous diagram, you can see that basically not only does our year-to-year and multi-year precipitation variability come from the largest storms, but they come, or at least they reflect our atmospheric rivers and Pineapple Express storms. So if we want to understand why we're in droughts historically, if we want to understand why we're in really wet periods in California, we have to be looking at the biggest storms. The presence or absence of those storms tells the story of why we get wet and why we get droughts. Okay, so the upper curve here, upper diagram here, is basically the same, back to the second slide I showed you, I guess, where, that's the observed total precipitation. Red is the largest storm's contribution, and green is everything else. And down below are doing the same thing to a couple of projections under the so-called RCP 8.5 scenario for a couple of different CMIP 5 or current generation climate models. And the wiggles aren't always so obvious in these models, although they do appear, you do get these occasional 10-year, 10, 14-year sort of bumps showing up. What I'm mostly want to show you here is that you get a similar sort of breakout in terms of the large storms are still the big part, a large part of the total precipitation and of the total precipitation variability on the scale of years. This diagram sort of makes that point. The stuff on the left here is just taking and saying what is the mean contribution in the historical part of these climate model simulations for 10 different models down at the bottom there, and observe the one that's standing to the left a little away from the others. What is the average amount of the total precipitation that comes from that top 5% in red versus the rest of the days in green? And you can see that the models and the observations all come in somewhat slightly, well, they're all generally a little bit below 40%, coming from just that top 5% of days versus everything else. And so to my eye, at least, there's some models get a little bit better compared to historical, some a little bit less. But fundamentally, that's not the models are kind of doing the right thing. This could be a lot worse. On the right here is for breaking out the year-to-year variance the same way. And in that case, we have to take into account that some of those wiggles are shared by both the small storms and the big storms. And so that's the blue stuff. But again, there's a bit more scatter more difference among some of the models from the observations here. But again, I really, when I made this diagram, was expecting it to be really ugly and really not very useful. But these aren't so bad, I think. Now, this complicated slide, and I'm not going to dive in too deeply. I will say that both of these diagrams are showing exactly the same data, sort of which way you would like to look at it. What's going on is that the black bars on the left there are changes in total precipitation for Northern California in projections by these 10 different models, and you can see the period, the time up there, the time difference, the windows that we're looking at the top. Green is, as usual, all the other days, and red is the red is 5% of days. And it's probably, to my eye at least, it's easier to look on the right, where I'm just plotting the contributions from either the red or the green versus on the x-axis versus the total precipitation, change in total precipitation on the y-axis. And the real story is down there at the bottom, that the largest storm contributions increase in 8 of the 10 models here, and I should say these are the 10 models that were identified as part of the DWR's Climate Change Technical Advisory Group that was mentioned in the plenaries this morning. Remaining storm contributions decline in all of the models. Largely, not largely, but that, one of the reasons why that happens is that the number of dry days increases in all of the models in the future projections for Northern California. And fundamentally, what's going on is we've alluded to today that about half of the models come in drier in the future, half of the models come in wetter in the future. And really what's going on here is all the models, most of the normal storms, the small storms, decline in all the models, their contribution to total precipitation. In nearly all of the models, 8 out of 10, the largest storm contributions increase. So in a lion's share of the models, the largest storm contributions increase. And whether we have a model that shows up with a total precipitation increase or a total precipitation decrease is all about whether or not the increase in the largest storms is enough to overcome that tendency for all the other storms to decline, their contribution to decline. Okay? That's saying that basically, we are seeing, some models getting wetter, some models getting drier. The way we will get wetter is by having our largest storms get larger. It's not exactly the way you might want to see it happen, but so, large storms are at best, a big important part of our future. You can play the same game with the year-to-year variance, how big those swings between wet and drought periods are, and the story ends up being largely the same. There's more scatter to it and the like. I think the bottom line really is the bottom line here, which is models with greater large storm variance increases end up yielding more year-to-year variability of the total precipitation. And the models and there are more models here where you do get declines in the year-to-year variance of the largest storms. Those, in every case, are ones where the year-to-year variance of the total precipitation also declines. What both of those slides are basically saying is the way that our precipitation in current models will change into the future is pretty much dictated by what happens to those largest storms, and it parallels what happens to those largest storms. So future of atmospheric rivers. Fundamentally, basically, at present, a warmer atmosphere holds more water, and so we end up seeing more storms that qualify as atmospheric rivers, and the intensities of them increase. You get relatively large increases in the numbers of atmospheric rivers making landfall in the projections. The average intensities of those storms increase, but it's really kind of marginal. It's not a big deal, 10%, maybe something like that. The maximum intensities of ARs each year do increase and considerably. And I would just note way down there in the lower right, Warner et al. Recently published a paper where they looked at much more extreme than what I'm looking at here. They had a cutoff that was whopper ARs. And they found that there would be like twice as many of what we would consider to be really hell-raising atmospheric rivers. So at the extreme end, you get large increases. That's something that we saw a hint of in 2011 in the previous generation of climate models, where there was a marginal increase in the intensity of the average atmospheric river, but we had already noticed that the biggest atmospheric rivers seem to really increase dramatically. So there aren't many of those biggest atmospheric rivers, but in the current projections, they do tend to intensify a lot. A lot of stuff here. I'm not even going to take you through, just say that we're looking at all sorts of things about these storms. And fundamentally, really, when you look at all these various things that are in the bullets down below, that point that the largest ARs really seem to kind of outstrip the others in terms of how much they change is probably the most notable, most newsworthy piece of information there. So I believe I'm probably out of time, but so basically what I've told you is that California droughts are really mostly due to missing big storms, with about 85 to 92%, depending on how you count it, of the annual precipitation variance being attributable to changes in the numbers and the contributions from the largest storms. There is a strong indicator, well, basically missing atmospheric rivers contribute disproportionately to the formation of our droughts, capturing about 75% of variance. This is a California thing. And for this session, I suppose the main thing is the projected changes in the mean and variance of precipitation for Northern California really ends up being dictated by what happens to our largest storms. So again, we would like it not to get drier, but there's a devil's bargain there. If it's not going to get drier in current models, that means we're going to be dealing with larger storms, depending on sort of which model nature might decide to somehow follow. And I will say, I've been showing you these wiggle diagrams all along, and any of you young pups out there, the big question I think that follows from this stuff is, what are those about? That's not El Nino, that's not PDO, that's, we don't understand what those wiggles are about, those 10 to 15 year long wiggles are about. Why should atmospheric rivers decide not to show up in many numbers for 5, 7 years at a pop? That's the big one, I think. So thank you very much.